This is lesson 1 in chapter 17, current and resistance. This is where our study of electricity really gets practical. You might remember from chemistry that electricity and chemistry are easily connected. You can use electricity to do chemistry, and you can use chemistry to create electricity. Batteries are electrochemical storage devices. Because of the design of the battery, which metals are being used, which material might be between the two metals, the size of the components, the concentration of any chemicals, all of these factors help to determine what the voltage of that battery would be and how much current would be possible to come from the battery. So electrochemistry, you recall, is the study of the relationship between using electricity to do a chemical task, which we called electrolytic cells, and using chemistry to make electricity, which we would call a voltaic cell or a battery. The voltaic cell, of course, comes from Alessandro Volta, Italian, and also Luigi Galvani. They made some of the very first electrochemical cells that generated some voltage. In fact, early on in the study, some 200 years ago, one of these researchers took a frog leg in a dissection and happened to use two different kinds of probes to pin each end of the frog leg muscle to a tray in order to study the muscle. But by virtue of using two different metals, which creates a potential difference, and then the wet muscle fiber in between the two metals would be the conducting material, there was actually a battery that was inadvertently made or serendipitously made, and that caused the muscle to twitch. And early on, that was called animal electricity, until they learned more and realized that what they had created was a battery. All you need for a battery, very simply, are two different kinds of metals, usually, and some conducting material in between. Hence, you have the idea of a driver or some other science-savvy individual finding two different kinds of metals, any type of conducting material in between, and you can use a potato or a dill pickle or an apple and the two kinds of metal stuck in it to become a battery. You can go online and see, for example, a battery or a lemon clock. Now, that's one way to create current. And of course, the whole idea here is to be able to control this process. So I'd like to make a couple of comments. You see the word destined here and the word control here. Of course, destined comes from the word destiny, and destiny has this idea of something that is inevitably going to happen. But I think more accurately, we ought to recognize the fact that in God's providence, human beings, if indeed they are fulfilling the cultural mandate to have dominion, that's where the word control comes in, to have dominion, they will discover patterns and relationships and the resulting applications to do all kinds of amazing things that are designed into God's creation and just waiting for us to discover. The other word I want to mention at the bottom of this page here is transformations. For example, the chemical energy in a battery can be transformed into heat energy, or it can be transformed into electrical energy that can maybe lift a weight by a motor off the ground, leaving behind potential energy. We'll be talking a lot more about energy transformations. Now, Current is going to be defined then as the amount of charge passing a given point in a given amount of time. We could call it a chunk of charge, if you like that phrase from an earlier screencast. So the average current is your change in the quantity of charge that is passing a given point in a certain amount of time. That's by definition right here. Notice a couple things. Inconveniently, we have the letter I to represent current. And we're going to be using ampere after the French physicist André Ampère to represent the term amps or amperes, which is the amount of charge per time. We would call it current. And the current can be direct current, like from a battery, or it can be the kind of current that goes back and forth called alternating current, which is the kind that you experience when you plug something into a wall outlet. And of course, Coulomb is named after the French physicist. So we have a rather international group of people helping to make this possible. So all currents then are basically average amounts of charge over a given period of time. And the instantaneous current would be where your calculus comes in, and that would be at a particular moment. The limit as your interval of time gets smaller and smaller and smaller. That would be your instantaneous current at that particular moment in time. So 1 ampere can be defined as 1 coulomb of charge passing through a given area in 1 second of time. Now we have another convention. Remember, we had electrical field lines always going from the positive to the negative. Later in chapter 19, we'll talk about magnetic field lines always going from north to south. In this convention, we are going to talk about current always going from the positive to the negative of a battery, and that current always being represented by the flow or the movement, we should say, of a positive charge. So typically it's easy to think about electricity as being electrons going physically through a wire, and that technically is not accurate. We want to think about the flow of positive charge, of chunks of charge, moving through a wire at near the speed of light. And we'll explain a little bit more about that later. Now, the direction of the current is always opposite, therefore, to the direction of the motion of the electrons. Since we've defined current as being the movement of a positive charge, that would imply then that the electrons are going to be going in the opposite direction. But they don't move very far, nor do they move very fast. And we've called that movement actually the drift velocity of those electrons, which is an interesting phenomenon. So the current is actually therefore moving in the same direction as the protons, and more technically, I would say, from the positive charge to the negative, because usually the protons are locked into their crystalline array or structure within the metal, unlike if you had a solution of positive and negative ions. Keep in mind that electricity requires there to be mobile charged particles, MCP, sort of a phrase that I invented for my honors chemistry students. And those mobile charged particles can be either electrons or ions. And these ions can actually come in two forms. They can be ions that are the result of dissolving a salt in water, and the polar water molecules yank the positive cations away from the negative anions. Or it could be a solid metal that has been heated up so hot that the metal melts. And then you can have, not metal, salt. The salt melts. And when the salt melts, then the positive and the negative ions can flow in opposite directions. Now, in electrostatics, the charges are stationary. But in an electrical circuit, where you have a potential difference applied across that circuit, in other words, the charged particles have the potential energy, when given the means to do so, to move through a wire. Those chunks of charge can travel through the wire, and as they move through the wire, every time they encounter a resistor of some type, and the resistor could be a physical object like a motor or a light bulb or a buzzer or a calculator display or any one of other hundreds of things. And a small amount of that resistance or work will have to be done just to go through the wire, but not much usually. By the time that chunk of charge gets all the way back to the negative post of the battery, all the way back to the other end, it is what I call PTO, plumb tuckered out. All charges will return to the battery with 0 voltage. And if there's very, very little resistance, then all of that voltage is used up in that little bit of resistance. And that little bit of resistance could burn out if it's not built to handle that much of a voltage change, or it could heat up a lot, or it might be designed to require a lot of voltage in order to operate. But all the charges return to the battery, plumb tuckered out, 0 voltage, and then the battery restores the charge, and then the charge can do it over again and over again and over again. So if you think about the idea that voltage is defined as the work per unit charge, when we come over here to this equation right here, our work, or our delta U, this type of energy of these charges, when we multiply both sides by Q, gives us the identity that this amount of work equals Q times the change in voltage. So here's a math problem. And in this math problem, we want to find the amount of charge that passes through the filament of a certain light bulb. Now, in a couple years, there will not be any more light bulbs which have filaments in them, that because the current is trying to plow through a high-resistance nichrome wire, it'll glow and produce light, but it actually produces more heat than light. The old-fashioned light bulbs that we still use are like that. They produce more heat than light, actually, and they get hot if you ever tried to unscrew one, if it just burned out and you're trying to replace it. They have a filament in it, but the new ways that we're producing light through light-emitting diodes and so forth are much cooler. They use less energy. They don't burn out as much. Right now, they're probably a little bit more expensive, but probably not for long. So in any case, this is a filament of a certain light bulb, and one of these days when they come up with the next edition of this book, that this problem will probably be obsolete. So we want to find the average current in the light bulb and the physical number of electrons, the actual number of electrons that pass through this filament or wire in 5 seconds. By the way, if you ever have a light bulb that is clear glass and you can see inside it, if it burns out, you can actually see that broken filament dangling down. And if you shake it a little bit, if it rattles, you know that the filament has been broken. So the first thing we're going to do is apply the definition of current. Charge divided by time. That gives me my amps. And we'll hold on to that piece of information and use it a little bit later on. Now, in the next part of the problem, if you remember right here, that current is defined as the amount of charge divided by time, charge per time, multiply both sides by t, and instead of using the pound sign for a number, use the capital letter N for the number of charged particles, each having a charge q. You get equation number 1 right there. And then we can solve this equation for N and plug our numbers in. Here's where we use the amp from earlier on, the amps. And we get 2.61 times 10 to the 19th electrons. And that's almost the reciprocal of this right here, which is the charge of a single electron. Finally, if you remember that volts is defined as work per unit charge, we can solve this equation for the amount of work, the delta U, and we get 20 joules of energy. We can take that 20 joules of energy, divide it by the 2 seconds of time, and now we have watts, remembering that a watt is a joule per second. All right, a little bit about drift velocity. Remember we said that by definition or convention, the charge is moving from the positive to the negative. So we're talking about the movement of the positive charge or chunks of charge. That would therefore mean that the electrons actually move in the opposite direction. And we distinguish here the difference between a macroscopic current and a microscopic charge carrier, like an electron. So the current's going one direction, the microscopic charge carriers, the mobile charged particles are moving in the opposite direction, and they're moving very, very erratically and irregularly as far as they can until they collide with something or are repelled by something. And to derive this next equation down here, we need to remember that volume can be considered as area times distance, or delta x. So looking at the picture up here, I think I'm going to change colors. We have our cross-section area and this distance x, and that gives us the volume of this piece of the wire. And so the volume equals A times delta x, and our charge is going to be our number of carriers, lowercase n, times the charge per carrier, and times my total volume, and we get the equation right here. And then if we divide both sides of the equation by t, my t is going to cancel out, and of course q over t is called I, and that's where we get this equation down here. N, charge, drift velocity, cross-sectional area of the wire, which you can sometimes get from the gauge of the wire. Interestingly enough, incidentally, the smaller the gauge, the thicker or greater the diameter of that wire. Now, by the way, keep in mind small v is velocity. Big V is voltage. The drift speed of these mobile charged particles is much smaller than a free electron that's not impeded or not blocked or not continually colliding with other electrons in the area. It's a very, very slow speed. It doesn't go very fast, as you'll see by an upcoming calculation. So this electron, and here's why, has a real hard time going from point A to point B because it's always colliding with things. It's kind of drifting around until it collides. It's going to move in the opposite direction of the electrical field. So if we look at example 17.2, we're asked to calculate both the drift speed and the RMS speed. Remember, RMS means root mean squared, because charged particles are moving left and right and front and back and up and down. We could talk about them having a positive velocity and a negative velocity, and it would not make any sense to therefore say all the velocities are canceling each other out because they have opposite directions. So we talk about squaring everything, which gets rid of the negative signs, and then we take the square root, that's where the word root comes in, to calculate their speed. Again, you might remember from chemistry, good old Avogadro's number, 6.022 times 10 to the 23rd. So to find the drift speed of the electrons in this copper wire, the first thing we're going to do is take advantage of the definition of density. Density is mass over volume. So therefore, volume equals mass over density. And that gives us our volume per mole. Once we have our volume in cubic centimeters per mole, we need to convert it into meters cubed per mole. And please note that just like there is 100 centimeters in a meter, there are 100 cubed centimeters cubed in a meter cubed. Very common for there to be a few people in every AP physics class I've ever taught to miss that conversion. And then you get a really weird number. So now we have meters cubed per mole. And then the next thing we're going to do is divide that into Avogadro's number. That gets my moles to cancel out, giving me electrons per meters cubed. So then we can take the equation we derived in the previous section, solving it for the drift velocity. And so we put our current, here's my current in the numerator, and in the denominator we have the number of electrons per meter cubed that we calculated, times Q, which is the charge of an electron, times the cross-sectional area of the wire, the thickness of the wire, and now we have our drift velocity. And notice it's about 2/10,000th of a meter per second. Not very much. Now if we come down here and take this equation from chapter 10 right here to find our root mean squared velocity, and here's my Boltzmann's constant right there, always given to you on a test. My temperature needs to be in Kelvin. Here's my mass of an electron. And notice that we get a speed of about 1/10 of a million meters per second. 1.15 times 10 to the 5 meters per second. So if you look at the difference between 10 to the 5th and 10 to the minus 4th, you get a billion, meaning that the drift speed of an electron is about a billionth of the actual speed of these electrons in the wire. Which means that it would take over an hour for an electron to manage to make its way through 1 meter of wire. So you might say, if it takes so long for these electrons to go through the wire, why is it that when you turn on a light switch, the light comes on instantaneously? Or any electrical device for that matter. And the good example is this. We go back to the concept of the flow of water through a pipe. And I did this in the first screencast way back in chapter 16, when we were talking about the water-electricity analogy. So imagine that I have all of these water drops. You could even talk about water molecules, or if you prefer, it might be easier to pretend, let's let every water molecule be represented by a marble or a BB. And let's say we have this pipe that we have jammed, filled with marbles or BBs. So you can't have any more marbles or BBs in that section of pipe. Now imagine you come along to one end of the pipe or hose and you jam a BB or marble in one side. Instantly, a BB or marble will have to fall out of the other side instantaneously. That's why we can say that even if the individual BB or marble or electron doesn't travel very far, the energy from that is seen at the other end instantaneously. There's instantaneously current that has a certain amount of energy. Now, current and voltage measurements in circuits. And of course, we've got a lab on this where we learn how to use a multimeter, pictured right here, that can measure different things depending upon how you set the dial. Or you can use a voltmeter and ammeter in order to find various things out about your circuit. So let's take a look at this circuit. And first of all, notice that we have to have a complete circuit, which means that you've got to have a pathway where your chunk of charge, which is got all of this energy, it's all pumped up, and it's going to leave here. It's going to travel through the wire, through the path of least resistance. It's going to encounter something to do work on, in this case, a light bulb. And the light bulb is going to emit light, which takes work, which means some of the energy is used up. The charge is going to get to the ammeter. It's going to go through the ammeter so that we can register the amount of current. Notice we're measuring the amount of current. It doesn't matter whether it's got lots of voltage or a little bit of voltage. Current is current. We check out the amount of current, and then by the time it comes here, it's plumb tuckered out. In other words, it has no energy left. Technically, it used up a little energy to plow through the wire. That's relatively inconsequential. Theoretically, it used up all of its energy going through the light bulb. Notice that in order to measure current, the current or ammeter has to be connected in series so that all the current goes through the ammeter. But the internal design of the ammeter is such that it doesn't take much voltage at all to make the ammeter, needle, or digital display work. Hardly any energy at all. And that's because inside the ammeter, it has got a shunt, which is basically pretty close to zero resistance. This omega symbol is a symbol for ohms of resistance. Now you might say, well, why didn't the current go through the voltmeter? Well, a very, very, very teeny tiny small fraction of current did go through the voltmeter. But the voltmeter is designed internally to have this huge resistance represented by this zigzag line. So this is the path of greatest resistance. But the little bit of current that goes through is what enables the voltmeter to move the meter or to light up the digital display to read voltage. Because of that huge resistor, almost all, 99.99% of the current goes this way. So voltmeters are always hooked up in parallel. If you do it wrong, you hook up a voltmeter in series, you can fry the voltmeter. And I want to make sure that I've covered everything that I want to here, because pretty soon we're going to get into Ohm's law, and I want to save that for a separate screencast. And here is where you are reminded that the circuit will work with or without the voltmeter, because the voltmeter is in parallel. In fact, as a rule of thumb, and I would suggest you follow this, when I set up a circuit with resistors and gadgets and gizmos and batteries and wires and so forth, I'll set up the entire circuit, including the ammeter, if there is one, And the very last thing I ever do is put the voltmeter in place, because all you have to do is take the two leads from that voltmeter and touch them on either side of the object whose voltage you want to measure. It's always hooked up in parallel. The other rule of thumb is when you are using meters or a multimeter is a multimeter because it can measure multiple things depending on how you set the dial. You always want to start off with, on the high side, assume a high voltage or a high current. And if you get very little reading or no reading at all, then adjust downward. And that way you can keep from frying out your device. We're going to end there, and our next screencast will pick up with Ohm's law.